Hello, my name is Neil Gunadiwal and this is my lab report. The purpose of this lab was to use a computational model to analyze the star's motion for all points along its trajectory to determine the mass of the black hole using its position, the star's mass and position, and the net forces calculated at each position. First, we will analyze the orbit of the star around a black hole and evaluate the net force along the trajectory. Momentum is a term used to describe a moving body, and impulse, the change in momentum, is calculated as F net times delta t. We will determine the mass using the momentum principle, F net equals impulse over time, and the universal law of gravitation, which is an attractive force from the center of a mass to another mass, calculated as the gravitational constant times the mass of the first object times the mass of the second object over radius squared. This is assuming that the net force of the star is due solely to the black hole located at the origin. The system is the star and the surroundings is the black hole. The net force can be broken down into parallel and perpendicular components, with the parallel component only accounting for a change in the magnitude of the momentum, which is non-zero if the object is slowing down or speeding up. The perpendicular component changes the direction of the momentum, so it is non-zero if it is curving or not moving in a straight line. For this lab, I used GlowScript to construct the simulation. First, I changed the seed line and replaced it with my personal school email, which ensured that the star had a unique trajectory. Then I plugged in the initial conditions. Mass of the star is given to be 2.0 times 10 to the 38 kilograms. The gravitational constant and delta t, which is calculated by the number of seconds in each day, which is 86,400. We set our initial and final momentums by multiplying the star's mass by the initial and final velocities. Then I set the change in momentum to equal p final minus p initial and change in velocity to equal v final minus v initial. P hat is the direction, and so it's a unit vector which is calculated by dividing the initial momentum by the magnitude of the initial momentum. To find the change in momentum and parallel direction, I used product rule to multiply p hat by the change in the magnitude of the momentum over delta t. For the perpendicular component, I subtracted this value from the total net force. In other words, dp over dt minus dp over dt parallel was my formula. Then I used this to manipulate the universal law of gravitation so the mass of the black hole equal the magnitude of the net force times the distance between the hole and the star squared all over gravitational constant g and the mass of the star. Lastly, we updated our arrows to be able to see the impact of the forces including F net, F parallel, and F net perpendicular. So this is my results after running the computer simulations, and it can be seen that the planet has a unique orbit around the black hole. The blue arrow represents the net force parallel, which is always in the direction anti-parallel or parallel to its instantaneous direction of motion. The magenta arrow represents F net perp, which is always focused towards the center of the kissing circle. And lastly, the orange arrow is the change in net force, which is faced towards the center of the black hole, which is larger when the radius between the two is smaller, as proved through the formula. After plugging in all the masses and data for the trajectory into an Excel sheet, I found that the average black hole mass over the entire trajectory was 1.33 times 10 to the 34th kilograms. The net force was found to equal 9.59 times 10 to the 28 newtons, the parallel component to be 3.56 times 10 to the 28 newtons, and the perpendicular component to be 8.93 times 10 to the 28 newtons. So what does this mean? Well, a net force is what causes a change in momentum, and it is always in the same direction as the change in momentum since time is a scalar. The parallel component determines the magnitude of the star's speed and will not change unless affected by an external force along its path, while the perpendicular component determines the direction of the star's movement and will remain the same unless affected by a force perpendicular to its trajectory. And what if the original black hole was removed and replaced by a new one? It would still not be possible to find the new mass. Due to consistent position values, trajectory, and mass of the star, the appearance of a different black hole will yield the same result. The velocity, momentum, and net force of the star will remain consistent, and since all other factors will remain constant, the mass will be the same when you plug it into the universal law of gravitation formula. Thank you.